Hey everyone, I'm Aryan, and today I'll be talking about what we call as nabla. One second. Yeah, so today we'll be talking about this thing called as nabla. Now, this inverted triangle which we have is known as nabla. Now, we'll understand what are the things which we can do with this nabla. So there are things like divergence, curl, and I'll be explaining what they mean physically, not just the mathematical interpretation. So now this nabla is an operator. Now, this nabla contains these three things: dou by dou x, dou by dou y, and dou by dou z. Now, these are the three things. Now, what do we mean by this? This is dou. Now, basically, we use this for something called as partial differentiation, right? Now, what do we mean by partial differentiation? In a nutshell, partial differentiation is when we try to find the derivative of the function with respect to a particular variable, keeping the others constant. So, for example, if I have this function x square y f of x comma y as x square y plus y cube x. Now, if I have to find the partial derivative here with respect to x, so dou by dou x of f of xy will be, I'll differentiate with respect to x here. So we get 2xy plus y cube. Now, one more time, if I have to find with respect to y, we'll have something of this sort. So x square plus 3y square x. Now, I think this makes the notion of partial derivatives clear. So we'll move on with what this nabla is. Now we have three components here: dou by dou x, dou by dou y, and dou by dou z, right? So basically, this dou by dou x is the partial derivative with respect to x, and the same for with respect to y and z, right? So we have two things which we call as the divergence and curl. Now I'll explain what divergence and curl is. So we'll first talk about divergence. So yeah, before I move on to divergence, so we have two types of fields. The first is a scalar field and the second is a vector field. Now, to illustrate a scalar field, let us say we are talking about the peak of a mountain, right? And this is about, let's say, 100 meters from the sea level. And let's say this region is about 90 meters from the sea level. This is about 85 meters from the sea level. Let's just assume if I have to plot it, I'll write something like this. So this is the peak 100. Now the region around it is 90, and I'll try to use different colors so that it is more clear. So like this region is 90, and if we go further from the peak, we have 85, and so on and so forth, right? So this will go on, and at the end, finally, this is the zero region. So we'll have zero, right? Yeah. So this is how we can kind of understand what a scalar field is. Now, what is a vector field? Vector fields are very useful when it comes to physics. We use them for fluid flow, aerodynamics is also part of fluid flow, etc. So yeah, it is a very important tool. For such, we also use vector fields when it comes to electrostatics, writing the or showing the electric and magnetic fields, etc. So if we have some fields like lines, I'm just drawing a random vector field. So this is a somewhat like a vector field. You can have any directions there. You, they're basically like we get solutions of differential equations, and these solutions basically lead to these vector fields. I'll just keep it there now. Moving on to the divergence. Now, what is the divergence? So basically, I just talked about this operator nabla, right? So nabla is defined as this. And let us say we need to find the divergence of this vector A. So A vector, let us say it has three components: AX, AY, AZ. Now divergence is basically the dot product. I'll use this notation. So the divergence is basically the dot product of nabla and A vector. So basically we know how we write A dot B, right? Mod A mod B cos theta. This is the dot product. So what the dot product basically tells us is that how well the vectors are aligned to each other, which means when A and B are on the same line in the same direction, the dot product will be maximum. And when they are perpendicular at 90 degrees, the dot product will be minimum, zero. It will not be minimum, it will be zero. It'll be minimum when it is anti-parallel, basically. Now, to write the dot product, we get something of this sort. This is what we call as a divergence. Now, what do we mean by divergence? So let us say we have something like this, right? We have a vector field. Let me make a field like this. I'm just making a rough diagram so that we can understand better, right? Now, we have a positive and a negative charge, right? So this is an electrostatic field. Now, we see that the positive charge, from the positive charge, the field lines are coming out. So this means that the positive charge is the source. And when we find the divergence of the electric field here, we'll get a positive value because the field lines are coming out. So the divergence basically means the how the field lines are diverging from a point. I'll explain what curl means later. So, and when we have the negative charge, we see that the field lines are basically terminating or coming towards the negative charge. So this acts as a sink. Now let that sink in for a moment. Yeah. So basically, we now established what source and sink are here, and this is basically what physically the divergence means. Now, when we speak about vector fields like this, let's say these we have vectors pointing like this. In a vector field, I'll not get into the mathematics here, but this is basically the 1 over r square function here, right? And this is basically how the electric fields look like for these charges. If we look at the formula, F equal to kqq by r square or E equal to kq by r square, we have the r squared function, right? Yeah. So that pretty well explains what divergence is. Now moving on to the curl. Now, what is curl? So I'll illustrate with the example of water because that is something that we see every day in our lives. Now, let us think of this example of water and we put a rotating fan around it, right? So the fan is rotating something like this. Now, what happens is, let us say the water was flowing like this, right? Now I put a fan here, right? So now when I rotate this fan, right, when I rotate the fan, the water around this fan forms a vortex. So what a vortex is, like, we have something of this sort. This was basically where the fan was. Now this is just a rough sketch. I'm trying to illustrate what happens, right? So when we rotate the fan, we get a vortex. So this is what we call a vortex. So this is basically what physically curl means. Curl basically, now if I rotate the fan in the clockwise direction, if I rotate the fan in the clockwise direction, the curl is downwards. If I rotate the fan in the anti-clockwise direction, the curl is upwards, right? So now the curl is defined as the cross product between nabla and the vector A. Now we all know how to do the cross product. We write the determinant of this matrix. Now here we first write dou by dou x, dou by dou y, dou by dou z, and we write ax, ay, az. If we do the determinant, we cancel the first row and the first column. So we get dou by dou y az minus dou by dou z ay I cap minus j cap dou by dou x az minus dou by dou z ax plus k cap dou by dou x ay minus dou by dou y ax. So this is basically the curl of the vector. Yeah, so basically we are done with the divergence and the curl. Sorry, divergence and the curl. So before I end this, I want to tell that basically when we perform the nabla operation, so operators are like something which is used to perform upon the given function or the vector. Now, when we perform the nabla operation on the vector, or we basically get, yeah, so now we basically have the dot product and the cross product, right? Now we all know that when we find a dot product, the final end product which we get is a scalar. And when we do the cross product, we again get a vector quantity. Now, similarly, we can see that when we do the divergence of a vector, when we find the divergence of a vector, basically we get a scalar field. But when we perform the curl of a vector, we get we basically get a vector field because the cross product always yields a vector. So yeah, this was the basic introduction of the nabla operator. So let's just summarize. We established what nabla is, and these are the components of nabla. Now I also explained what dou is. Dou is basically used for partial differentiation. I gave an example of how partial differentiation works. Then I explained what scalar fields and vector fields are. Now, then we moved on towards divergence and curl. I explained what divergence is, right? We did the dot product and I explained what it physically means. I also explained the 1 over r squared function for electrostatic charges. Then we saw what curl means. Before that I also gave the physical example. Then I solved the determinant for this. And yeah, that's what concludes this basic introduction of what curl and divergence basically means. So yeah, thank you everyone. See you next time.